And then next week I have lab. Sorry, so I don't have the whole day to figure out what I'm doing now. Tomorrow. It shouldn't go.
Okay. Audio's working. Okay, good. All right. Okay, let's get started. How y'all doing? Good morning. It is a great morning. You like Lab 1? Oh, you're so far behind already. I hope you're already neck deep into Lab 1, because if you're not, you're behind. Okay, boards are available for checkout. Overnight checkout, you just go and talk to Heidi. You got to give up your card and firstborn child, and she will let you have a board overnight. Okay. Don't have one of those, unfortunate. So, yeah. Several of you were in lab yesterday, took advantage of having Rohit available to answer questions. I dropped way too many hints yesterday, unfortunately. Benefits of actually going to lab. I don't feel at all guilty for those of you who skipped. Sorry. Go to lab. Okay. Anybody have any questions? Mitch.
Do we know when the keys are going to be available for that room?
I don't know when the keys are going to be available. Heidi is in greasing the skids and had talked to the lock shop person, and so hopefully soon. But like I said, you should be good to go for home development. And for the most part, the vast majority of this lab you can and should be doing outside of without a board. The compression algorithm will be much better developed if you write your own decompressor and run it on the host and use your traditional development and debugging skills that you've already developed and already figured out how to do. Okay? By far, the most time-consuming part of this lab is the compression. Okay? There are several questions associated with Phase 2 that you have to address, which seem pretty innocent, but they're not. I would suggest that you attempt to address those after you get the compression working, because the compression will force you to learn every ounce of VIN to FLD very well, and you'll need that information when you attempt to answer the questions that are in Phase 2. Okay, Brad.
We're not writing a decompression, though, right? We're writing a compression.
You're not required to write. So the question is, we're not writing the decompression as opposed to the compression. You're not required to write a decompressor.
Because it already has one.
The board will do the decompression. The bootloader code already does the decompression. It is much simpler if you attempt to decompress on the host. If you write your own decompressor, that's a better way of doing this. I'm not making you write a decompressor, but I'm saying you should. Okay? It's also helpful if you write a diff utility. So if you take a file, you compress it and decompress it, having a diff utility will allow you to compare the file that you decompressed against your original, and that'll tell you where the errors are. These are things to help you be more productive in your compile, execute, debug, figure out if it works. Your diff utility is like your blinking LEDs. Will tell you whether or not your system's going to work. Okay? So these are helpful hints, and those students in the past who have actually written the decompressor and written a diff utility and done development in that fashion, they've been much more successful at getting things to work as compared to those who decided to just use the board to do the debugging. Okay. We are going to be digging through more details. That's all we do in this class is dig into details. We've been talking about loaders. We'll continue to talk about loaders and the approach for loading. Loaders make a good context for teaching you how computers really work. And that's really the context of this discussion. is how does a computer really work? You've never had to think about what is a loader because you just double-click on a program or type in the name of the program and the program runs. You never had to pay attention to the fact that the operating system actually loads your program and does some stuff beforehand before you actually run any program. So you guys have been running loaders for years now, but you've never had to pay attention to that fact. That's one layer of the onion you typically get to ignore. Well, for embedded system development, we can't ignore it. So let me just throw this figure. I've shown this figure a bunch of times before. You remember that we have standard approach for doing development, which is you edit your code, you build it, and then you run it, you see if it works, and then you edit your code again. So over here, in our embedded development, we have to use cross-compilers, okay? So we have cross-development where we cross-compile, cross-assemble, cross-link. Then we have our loaders, a host side loader, a target side loader. We execute it after we're done loading. We watch the LEDs blink, and then that gives us information to go back and modify our program, figure out if it's working or not, where to tweak it, and then we move on from there. Okay? So we talked a little bit about what's this business of loading, where we got this host side loader, and I told you we have to prepare our file, the executable file, the output of our cross-linker. We can't really load that directly. The reason why is because the bootloader I'm providing you does not understand the file format that the linker outputs, because that linker file format contains some metadata. I'm going to talk about linking. We might get to it today, we might get to it next time, depending on how things go. But I'll talk about what is that file format, what does it contain, and what is the linker's job. But just take it for right now that there are some metadata, some meta information contained in the linker file that tells the loader what to do. Okay? Our loader is a very simple loader. All it does is it says, I'll take bytes from the serial port, I'll put them into memory. It doesn't know how to rearrange the bytes, to initialize sections, to load this here and that there, and relocate things. It can't deal with like dynamic linking or other fancy things. The file format that the linker, the cross-linker outputs, supports all those features. And so we have to extract and throw out all that information. So we have to chew on the file format a little bit before we can actually deploy it to our host side loader. Okay. The way that we chew on it is like this. So ELF is the name of the output file that's output by our cross-linker tool. Okay, so p.elf. We have a program called p.c, which just does a forever loop that prints out a few numbers and a few strings, and when you run it on the board, it just scrolls up on the screen. Several of you saw that output before. Didn't I show you that program running last time? So it looks pretty much the same when you run it on the host as when you run it on the board. Okay. P.elf is the executable file that the cross-linker outputs. We have to send it through object copy to remove all this header information, this meta instruction, the metadata associated with the executable file. This effectively loads the program into the PC's memory. Obviously, we can't run it on the PC because the program here is targeting ARM. But we're going to pretend that we have an ARM for a minute, load it in the program's memory, then take a snapshot of that and save it in a binary file. That's p.bin. We will also extract the header information with this system-provided readelf file that extracts header information and puts it into a file called p.config. Both of those two files go into bin2fld, the source code of this program I provide you, and this is where you're going to put your compression. Okay? So this guy takes p.bin a chunk at a time, provides a header byte for it, and outputs it to the output file, the FLD output file. The p.config file is mined for a couple of pieces of information, the load address and the entry point. Those are stored in the FLD file as the first 8 bytes. Okay? So p.fld is our output file, which contains the header information that we need to tell the executable, and it also contains the packetized version of the p.bin. That FLD file then represents the executable file that we're going to load onto our board in the file format that our host side and target side loaders can understand. We then send it through fld.exe, which is our host side loader, and that talks via the serial port over to the target side loader, and that gets our program into the target side memory, and we can jump to the start address of the target of the program after we load it. Okay? Mitch?
To get at these notes, do we have to just watch this replay again?
No, I post them. I just haven't posted this. So, okay, the question is, do we have to watch the replay in order to get to the notes? No. Under Blackboard, under archived lectures, I post the Microsoft Journal files.
After the lecture, before
After the lecture. Simply because right before the lecture I may tweak things. And I've already have one instance this semester where my notes that I've already posted aren't synced up with what I actually gave out. So I've got to fix that. And so I usually post the notes of what I present after I present them. Okay. So the task today is to show you how the makefile does this build process. It does the cross-compiler, cross-link, and all of that, and how that makefile does all of this business. Okay? Now, there's a lot going on there, and fortunately or unfortunately, you got to understand how the makefile does this and what in the world it's doing, and you got to understand why. Because when you're doing your compression stuff, all of that you have to keep straight. Okay, so last time we talked about the whole point about, I reiterated this over and over again about the fact that we need to do all this massaging of the executable file. Here is the makefile. Okay. So this is the script that builds p.elf, p.bin, p.fld. It also builds the host side loader. It also builds bin to FLD. Okay? All of this stuff is contained in this one makefile. This makefile invokes different compilers. Okay? So there's two different compilers that we invoke. One of them is the Visual Studio compiler. The other is the cross compiler. We need to have two of them because we're building two kinds of programs. One kind of program runs on the host. One kind of program runs on the target. For anything that runs on the target, we use cross compiler. For anything that runs on the host, we use Visual Studio. Okay? Why don't we use the native GCC to build the host side code? That's because some of the serial port code that I build for you, that I give to you guys, that accesses the serial port for doing the host side loader, is specific to Windows and uses Microsoft header files. So that code can't be built with GCC. Sorry. So I'm going to show you how you use one makefile that can be used to build both programs that run on the host, programs that run on the target, and how it can be used to run those programs. Okay, first off, these right here at the top of the file, this capcc and cap obj copy and all of that. What this is defining. These are defining variables in our makefile. These are just placeholders that we're going to use that we expand later on down here in the statements that use them. Think about those as pound defines. Okay. The reason why we're doing this is the same reason why you use a pound define. We're associating a symbolic name with some other name. Maybe it's because we're going to use this symbol in multiple locations, and maybe later on we want to change that symbol name, or what the symbol name binds to, and it'll make it easier to just change it once instead of having to change it in 14 million locations throughout a program or throughout a makefile. But we're just associating, you think about them as macros or just as variables. Okay? In makefile terminology, these are variables. Okay? And if you want to instantiate the variable or dereference the variable or grab the thing that the variable is supposed to be associated with, use a $ parenthesis followed by the variable name followed by a close parenthesis. Okay? And you'll see uses of that, like here where it says $CC and $C flags. This is where we're using, instead of, we want the makefile to replace $parenthesis CC close parenthesis with whatever CC is associated with, so armelf GCC. So make will go through and take this $CC and replace it with armelf GCC. Okay? So these are variables. We'll tell exactly what those variables mean as we get down over here. Now we have this next section right here where it says .c.o colon, .c.s and .s.o. These are a sequence of implicit rules. Okay? If I had a program that depends on, maybe 10 different .o files, and each of those .o files are built from a corresponding .c file, if I'm just using bland makefiles with no implicit rules or anything like that, I would have to create a target for each one of those C files. The rule associated with each one of those C files is exactly the same thing. Run the compiler, build the object file. Run the compiler, build the object file. Run the compiler, build the object file. These implicit rules allow me to say, for any time I have a dependence down here in my targets and my rules on a .o file, if I have a corresponding .c file, this rule is good enough. Okay? So this says anytime I need a .o file and I have a .c file, run whatever the CC variable points to, which is RMLF GCC, pass it the flag -C, instantiate the C flags. C flags up here, if we look up C flag, says -02, $, less than. What $, less than means is take the .c file as our input. Funky little syntax. Okay? So this says if I want to create P.O from P.C, run RMLF GCC -C -02 P.C. And that will create P.O. Okay. The next rule says -C.C.S. What this says, if I need a .S file and I have a .C file, run the cross compiler, pass it the switch -S -C -02 to the C file, so forth. Okay. So all these things are implicit rules, and I can use them just to say I want to have this generic rule in here for building any .o file that I might need, as long as I have a corresponding .c file. And down here below the implicit rules, I have the all target, and the all has P.FLD and FLD.exe. So those are the two targets that all depends on. All doesn't have any rules. So if I want P.FLD, I've got to go find a target that says P.FLD, which is down here. P.FLD target : depends on P.bin, P.config, and bin to FLD.exe. Well, if P.FLD needs P.bin, how do I get P.bin? P.bin is this rule that's right above the P.FLD rule. So P.bin is the target : it depends on P.elf. How do I get P.elf? P.elf is defined here in this next target up. P.elf depends on OBJs, LD script, and makefile. OBJs is this right here, P.o. So $OBJs expands to P.o. So P.elf needs P.o. It also needs LD script. LD script is a variable here that expands to armelf.x. And it also depends on makefile. Okay? So if the makefile gets changed, then that rule will get run again. Okay? If P.o gets changed since the last time I built P.elf, the rules will run again. Likewise with the armelf.x script. And I'll explain what armelf.x is all about in a minute. Okay, P.elf depends on P.o. Where do I get P.o? I don't have a rule in the makefile for P.o, so I go up and I check my implicit rule. I do have an implicit rule right here that says if I need a P.o and I have a P.c, then run the cross compiler on the P.c file to produce P.o. So the dependence right here, P.elf on P.o, causes the implicit rule to run. I run the cross compiler, I build the object file, and then if the linkage editor script and the makefile are both up to date, then I run the rule associated with P.elf in order to build P.elf. What this rule says is run the cross compiler, RMLF GCC. Again, I'm going to do a link step here, but since this is a port of GCC, and as I told you before, GCC is a compiler shell that invokes other programs, I use it to invoke both the compiler and the linker. So I'm using it in this context here to invoke the linker. So I'm saying $CC, $C flags, $C flags expands here to -02. Well, when you say -02, that's a compiler flag, not a linker flag, so the linker will ignore it. -xlinker, -t, -xlinker, $LD script. Okay. -xlinker is a flag that you pass to GCC, which is the compiler shell that tells it, take the parameter that I'm passing to you next and forward it on to the linker. So this tells GCC to take -c and send it to LD, the linker. So I'm saying -t, -xlinker, LD script. So GCC will pass -t, armelf.x onto the linker. Kind of clunky when you're using GCC. You have to tell it for each individual switch that you want to pass onto your linker. These two go together. The -t, armelf.x go together, but because they're separate parameters, I have to tell GCC to pass them both to the linker with the -x linker command. So, and what the -t says is I want to use a particular linkage editor script, and that's what armelf.x is. And again, I'll talk about that a little bit more when we talk about linkers. Next, we say -x linker -map -x linker p.map. This tells the linker I want to produce a map file, and I want the map file to be named p.map. And I'll tell you what the map file is. Map file is how the linker tells you what it went and did with itself. Okay? This is a very important file for Lab 1. -o p.elf, that says whatever you're going to do, you're going to produce an output file, rename it to be p.elf, and this is the inputs to the linker, $objs, which expands to p.o. That's all it is. Pretty simple, huh? That's all you need to do to link a program. And regurgitate that for an exam, right? Well, anyway. So, what we're doing is we're just linking p.o to be an executable file, and that produces p.elf. So great. How did we get to this point again? You remember if we say make, that builds p.fld, p.fld needs p.bin, p.bin needs p.elf, p.elf is that thing we just talked about. So now that we have a p.elf, how do we get a p.bin? P.bin right here, we've satisfied the dependence. This is crazy. I've got two computers and both of them have screensavers. Okay. Here, p.bin. The dependence is up to date now. So how do we get p.bin? $obj copy. We pick that from our variable that runs armelf object copy -r-s-o binary p.elf p.bin. Remember I showed you this line last time. Okay. So that says massage this executable, throw out all the metadata, throw out all the sections, produce a binary file, and that causes object copy to load the else file into memory, then take the snapshot of that, latch it back down to a file, and it saves it in the p.bin. Okay? We also run this rule right next where we say readelf -h p.elf, and then we redirect the output to be p.config. What this does is it runs the readelf program, which will read an else file. -h means I want to read the header information. I want to extract the header information. Where's the else file? It's p.elf. Readelf by default throws its output to the screen. So it's throwing its output to standard out. So we say, okay, don't throw it to standard out. I want you to throw it to a file. So I use this greater than here to redirect the output to a file. So that's what p.config is. You are going to need to read that file. Okay? That's a text file. You can open it. You can read it. bin2fld also reads that file. You got to know what that file is saying. And it's just a simple text file. It's got maybe 20 lines in it. Okay? So now what that gives us is both p.bin and p.config. By the way, if you run the make file, I'll show you what it does. Understand the make file. I don't know what you mean. I'm explaining you the make file. Okay, you can't have warnings. You can't have errors. And I've given you some. So congratulations, you got to get rid of them. All right. Okay, you see this error right here? It says, warning, clock skew detected, your build may be incomplete. That's another one you got to get rid of. I'll tell you how to do it. Just because otherwise all y'all are going to be in my office saying, how do you do that? It's caused because this readelf right here. So readelf right here is a rule that's in the same, it's caused by the fact that p.fld depends on p.bin and p.config. We don't have a separate rule for p.config. We just build it when we run p.bin. Okay, so if you create a target for p.config and put the readout rule in that target, that clock skew error goes away. Okay, so now we know how to get the bin file. How do we get the FLD file? The FLD file depends on p.bin, p.config, bin to fld.exe. We've built p.bin, we've built p.config. We now depend on bin to fld.exe. This is a program that runs on the host, not on the target. I cannot use the cross compiler to build it because I'm building for the host. So how do I get bin to fld.exe? I come down here to my target, bin to fld.exe, that depends on bin to fld.c, which is a file that I've provided for you. I run cl/w3 bin to fld.c. What is cl? That's Visual Studio's compiler. Okay? When you download and put the cross-compiler tools on your system, I've got a setup.bat file that I talked about in the lab write-up. That batch file sets up some paths and invokes a particular batch file. That batch file is called vcvars32.bat or vcvarsall.bat. That's a batch file that is created when you install Visual Studio on your computer. That is a batch file that contains a bunch of variable definitions and header paths that get to be defined as part of the Windows environment if you want to run command line compilation tools using Visual Studio. Okay? So the setup.bat file that I give you invokes Visual Studio's vcvarsall.bat file. If you've monkeyed around with where you put your Visual Studio installation when you installed it, you've got to tell my batch file where you put that batch file. Okay? So just my setup.bat file is about 5 lines, and you just got to edit the spot in the right spot, and it'll and point it to where you put the vcvars file and where you put the cross-compiler tools. So now that I've sufficiently confused everybody with that last statement, let me show you the batch file. Okay, this is the batch file I'm talking about. So when you, on Blackboard, there's a tstools.tgz file. You download that sucker, you put it into some folder on your machine, you open up Cygwin, you say tar-xvzf tstools.tgz. That's how you extract and unzip that gzip tarball, and that expands to this folder over here that has an install folder. Right here, the first thing you got to do is set up a path to where you've got your cross-compiler tools installed. On this machine, I've got them on CEC5780 tstools install bin. You got to change this path to wherever you put your cross-compiler on your computer. Okay? So if you put it in documents and settings, I love Microsoft /EC5780, you got to replace this path with that. Make sure you have the /bin on the end. Okay. The next line is where you tell it where the vcvarsall file is. In the lab write-up, I told you where some default locations of various versions of Visual Studio where you find the vcvarsall file. But where it's at, depending on if you monkeyed around with where you installed Visual Studio on your computer. If you have trouble with this, let me know. The next thing this does is it invokes Cygwin. So in order to run the cross-compiler, you got to double-click on that setup.bat file, and that will bring up a Cygwin prompt. And then you can run make within the Cygwin prompt. If you open Cygwin under the way you've typically opened it, just with the Cygwin icon that's on your desktop after Cygwin installs itself, it's going to say, I can't find the cross-compiler. So you have to use the setup file to open up a Cygwin prompt that has the paths set up so that you can run the cross-compiler appropriately. Because Cygwin doesn't know where the cross-compiler is by default. Okay. That vcvarsall file is critical to be able to run CL on the command line. If you don't run that in the right environment, in the proper context, you can't run the native compiler Visual Studio on the command line. So only by virtue of the fact that we ran that batch file do we get the ability to run CL on the command line. So once we do this, CL/W3, this is the same thing as saying, this turns warning level 3 on for Visual Studio. That just builds bin to FLD.c, or bin to FLD.exe from bin to FLD.c. Now we have bin to FLD.exe. So this rule, the dependencies for the p.fld target, p.bin, check, p.cfd, check, bin to FLD.exe, check. Now I can run the rule. And then we run the rule by running the program. Some of you are asking, how do you run a program in a makefile? Here's how. You just have a rule that runs a program. You just invoke the program right here, bin to FLD, p.config, p.bin, p.fld. So bin to FLD takes 3 input parameters. One is the config file, the next is the bin file, the third is the output file. Okay? So this takes these 2 files, p.config and p.bin, and produces p.fld. Great. We now have our output file. This is the program that we can now run on our host side loader or run through our host side loader to put it onto a board. So going back up to all, we depend on p.fld. We've just successfully built p.fld. Now we need to build fld.exe. That is much less involved. All you do is you just say, okay, you want fld.exe, you take fld.c, you run Microsoft compiler on fld.c, and that gives you fld.exe. So now you have the program you want to load, and you have the loader. The other entry in the make file is clean, where clean just has a bunch of rules for how you delete any intermediate stuff that you don't want that are artifacts of the build process. So I just included these rules for removing anything as a .else, .o, .s, map, other things that you can see there. Okay, questions about the make file? Just remember what the goal of that sucker is. It does this thing that we saw up here, amongst other things. It takes your else file here, and it produces p.fld, and it produces fld.exe. It does not run the loader, it just gets ready to run the loader. It gives you the loader program, and it gives you the program you're going to load. Okay, now because I know that there is no possible way that you can keep in your head what it was that I just all talked about, the next section in the notes goes through line by line in the make file, and it explains what's going on. Okay? Hello, Limba. Let's catch up. There we go. So it says, here's your cross-linking step, and it explains the dependencies, and it explains what's going on in here. So, for example, the armelse.x file is a linker script that tells the linker what to do, what to put where. We'll talk about that maybe today, maybe next time. Okay, so there's the linkage editor script talking about dependencies, expanding the variables, dash x linker and all that stuff. Let me mention again the map file. The map file tells you what the linker put where in the address space. So the linkage editor script, armelse.x, is an input file to the linker. The map file is an output file from the linker. You do not need a map file in order to run your executable. Map files are not unique to cross-compilers. You can have GCC that you run for your host computer produce a map file. You can have Visual Studio produce a map file. This is just a file that a linker will output that it tells you, well, I have these symbols, and I put them at these addresses. And it'll also list, these are the addresses that I touched, and this is what I put there. Okay, so it's a cross-index, like a phone book and a backwards phone book that it tells you, this is what I put, this is where I linked these symbols to which addresses. Okay. Now, looking at the p.c file, this is the program we're building that we're going to run on the target. We include stdio.h. We declare 2 global variables, b and a. We initialize a to 0x55. We have the main program here, the main function. And we have stupid screensavers. A forever loop here. This never terminates. By the way, when you're programming embedded systems, that's typical. You typically have a program that doesn't ever return, because what will your embedded system do if it did? You know, what happens if your analog break program returned? Okay, I've done enough breaking for today. You're on your own. Okay, so forever loop, we increment b by 10. What's b's initial value? Somebody show me the assignment to 0. Is there an assignment to, is there an initialization of B in this file? No. Very curious. Okay. But we increment it by 10 anyway. And then we print %s. %s says take something off of the list of variables that I have and print it as a string. Print the character B equals. Then %d says take the next variable off the string, off the set of variables and print it as a base 10 integer. Then print A equals 0x. %x says take the next guy, interpret it as an unsigned integer, print it in hex. Address of $A, these again are just characters that get printed. %x then says give me whatever on the list of variables, print it in hex. Main equals %x\n. So I've already said what %x does. The list of variables are __file__. This is a preprocessor string. That preprocessor macro expands to the name of the file that's being compiled. So file expands to p.c in double quotes. Okay? So the preprocessor does that replacement. So when you say %s:, that'll put p.c:. If I rename my file to fred.c, it'll put a fred.c right there. $A main. Okay, so B, I print out the value of the global variables B. A over here, I say A equals 0x %x. I print out the value of the global variable A in hex. Then I say address of A equals %x, and I pass address of A. So that'll take the address of A as an unsigned integer, and it'll print that in hex. And then it'll say main equals %x, and I pass main. Can you print main? How do you get a pointer to a function? What do you mean you can print a pointer to it? And am I printing a pointer? What does this say? %x says interpret whatever's there as an unsigned integer and print it in hex. So this right here, so I say int main void. That means main's an int, right? Because I've got int right next to main. Yes? No? Returns an int. Is main an int? It's a dealie. One blessed little dealie. The thingamabottle. What's it? How can I print main as an integer? It's not an integer. It's a function. So is this going to make it print out the this code here? If I say I want to print out main, will it just print out the C file? Do you know how to make a program that prints itself out? That'd be a great test question. Okay, that's an aside. What's that going to do? All right. Let's run it and find out. Done deal. Okay, so it scrolls a whole bunch of outputs. This is running on the host because I don't have a target nor a serial port on the tablet. So here's p.c, b equals this value. What do you see the value of b doing? Incrementing by 10 each time. Then I have a equals 0x55. Address of a is 402000. Main equals 40105. Well, that doesn't look like count include stdio.h. It's an address. What's it an address of? It's an address of where it starts. It is one of these lovely ambiguous terms. What is it? It's the address of where the first instruction of main starts. The main function. The address of where the main function starts? You guys know what you're trying to say. It's just you're struggling for the right words here. The address of the first instruction of main would be the proper phrase. Okay? Okay. Where do we decide what the address of main should be? Well, it depends on what the definition of we is. We, the computer science programmer, never has to worry about this. We, the computer engineer, who has to peel back the layers of the onion, has to say, you know what? The cross-compiler and the linker and the loader, they are all my friends, or my minions, or anyway, you can say they belong to you. So we includes all your build tools. So where do we put main? And how do you know where we put main? Who decides what goes where? The linker decides what goes where. Okay? So how do you know what the linker went and did with itself? Oh, maybe that has something to do with why I've been dropping hints about you need to look at p.map a whole bunch. Yeah. Convenient. Okay. Okay, so here's just an explanation of what's going on. And this command right here, gcc p.c-o, p.exe, that's what I just showed you. Okay. I'm tempted to jump into the linker lecture right now, but let's just finish talking about these other programs here. So keep your appetites wet for p.map. I'll talk about that one next time. Meantime, we're going to talk about bootloader. Okay, bootloader.c. What is bootloader.c? It's a file. Good. That is actually the correct answer. It is a file. What does it contain? Does it contain a program? It contains code. What's code? Okay. Anyway, semantics are always fun. We'll debate them later. This contains source code for a program that we will build from it. Okay. What is the source code? What's the source code intended to do? Is it host side loader? Target side program? What is this thing? This is the source code to the target side of the loader. Okay. So this does a lot of things. It configures the serial port, but when it gets down to here, what we're going to do is I'm going to get a size byte from the serial port. Get.ch is a function that's defined in bootloader.c that acquires a byte from the serial port. So it gets a byte, and it says that byte's a size byte. So while size, if size bitwise AND with 0x80, if size and 0x80, then do this, else do that. For uncompressed packets, we're doing this, like I told you about before. So while size, decrement size as we go along, get a byte from the serial port, copy it to the load address ++, and then do it again and again and again until size is empty. As soon as size is empty, then I go down here and get another size byte, check to see if size is 0. If it's not 0, check to see if it's compressed packet or uncompressed packet. It's an uncompressed packet until you guys implement compression. And we do this again. We just get the sequence of bytes from the serial port and copy them to where we're copying them to, starting at the load address and going on forward. Okay? So as soon as I get a size byte of 0, I come down here and I invoke function pointer. Function pointer points to entry point. So this just causes me to jump to the entry point. So that's what the bootloader does. What you got to think about is this is what your target is doing. Your host side loader has to do the same thing, except for instead of receiving the packets, it's got to send the packets. Okay? So I've got to grab a size byte and download it, and I've got to grab the data bytes and download them. Then it's the next size byte, download, data bytes, download. So this is what we're going to do, is looking at FLD.C right here. Okay, so this is the FLD program, the host side of the loader. Init com1 is a function call that I make that is to a function that's defined within this program here that invokes the Windows stuff to set up the serial port. Okay? And that code already works. You don't have to worry about how it's implemented too much unless you're one of the masochists who wants to go and implement this on Linux. Okay? I'm past 2 command line arguments. The 2 command line arguments are, number 1, the name of the program, number 2, the name of the program I'm downloading. So every program always has 1 command line argument, and that's the name of the executable program that's actually running. The second command line argument is the name of the program that I want to download. So I open it. RB says open the file, argv1. RB means for read mode in binary. So I'm assuming there's a binary file. Okay? Then I print out, please reset the board. And then while buffer sub 0 is not equal to pound, read a buffer, serial read is a function that I provide in this file that reads the serial port. So I'm going to read 1 byte from the serial port, put it in the buffer, and I'm going to wait until I get from the serial port the character pound. So those of you who have been in the lab and have run the bootloader and saw on Hyperterm, when your bootloader works and you see that little pound character, that's a character that's uploaded from the board that's saying, I'm ready to receive a program. So FLD waits until it receives the pound from the board, indicating that the board's ready to receive a program. Okay, loading program. What I do is I read 8 bytes from my input file. This is my FLD file that I'm reading from, and I put it into buffer. Then I serial write 8 bytes from buffer. So I take the first 8 bytes of my FLD file and I download them to the board just verbatim. Okay, you need to figure out what those 8 bytes contain. You need to figure out where those 8 bytes came from and how they got into the file in the first place. Then, while not in the file, get a byte. Write a byte. If that byte is not equal to 0, sleep 1, then read however many bytes that byte indicated and write that buffer. So, for uncompressed packets, you're going to have a packet that is 127 bytes long, followed by the 127 bytes that you want to download. Okay? So, this S is the size byte you read from the file. So you're going to read 1 byte from the file. It will indicate how many bytes are in the next packet. You read that many bytes out of the file, and you'll download the byte. So you download the size byte, then you download the packet. Then you read the size byte from the file, download the size byte, read size bytes from the file, download those bytes. Okay? So this is just reading the file and downloading it, reading the file and downloading it, 1 packet at a time. The target side is going to read a size byte and accept size bytes from the serial port. Okay? Does this make sense? Replete with comments? Okay. Bin to FLD. So this is our compressor utility, or our reformatter utility, however you want to call it. So what I have here, a bunch of fputcs. Fputc takes a byte and puts it into an output file. Okay, so I take load address, load address, load address, load address, put 1 byte at a time in my output file. Entry point, entry point, entry point, entry point, put those into the output file. Then I equals 127. While I greater than 0, put I, which is 127, to the output file. Read from my input file. Again, this is bin to FLD. This is taking your input file, your bin file, and it's outputting the FLD file. So I'm going to take 127 bytes from my input file, put those into buffer, and I'm going to output buffer, which contains 127 bytes, into my output file. So take 127 bytes from my output file, put in the number 127 into my output file, put in 127 bytes, then do it again. So put the number 127 to the output file, followed by 127 bytes that I read from my input file, and so forth, until you get to a size of packet until you don't have 127 bytes left in your input file. As soon as you don't have 127 bytes left in your input file, you just put whatever you got left. The last thing you put is a size byte of 0. Okay? Each iteration of that loop writes 1 packet. All right. This is kind of what your file is going to look like. You got 127 followed by 127 bytes, 127 followed by 127 bytes, followed by the end of the file. You may have something like a 3 followed by 3 bytes. This is the leftovers. B sub ij, you see BN0. This is the ICE packet, chase entry in the packet. You always have bytes 0 up to 126. Okay. Couple of hints. Our packets are up to 127 bytes in length. In binary, it takes a total of 7 bits to represent all the numbers between 0 and 127. We never use bit number 7, which is the 8th bit. So that's available for other uses. Okay. What can we use it for? Good question. Okay, Visual Studio can show you the contents of a binary file. If you just take a .bin file and drag it and drop it onto Visual Studio, it will open up a hex editor and show you a hex dump of the file. FLD, you can dump a FLD file, and it will show you the contents of the file as if it were just a regular binary file. You can't do it with .exe. You have to change the extension. Okay? Another hint, you got to create some input files when you're testing your compressor. Hack lab 0 to generate test input files. Might as well use code you've already got. Run it on the board only when you think you've got it working. Try to do your development on the host. Write a compressor and a diff utility. Okay, I'm done. You have the guns now to do lab 1. We'll talk about linkers next time and then proceed on with chapter 2, followed by chapter 3. Makes you think you're going to need the lab.
Maybe.
Nope. You'll need it. I'm sure you don't have an oscilloscope at home.
No, I don't.